For decades, astronomers dreamed of seeing the dawn of time, the very first stars igniting after the Big Bang. But the Hubble Space Telescope, for all its power, couldn't pierce that veil. To do it, humanity would need a new kind of eye on the universe, the James Webb Space Telescope. It had to be bigger than Hubble, colder than deep space, and somehow fold like origami to fit inside a rocket. The engineering was a monumental task that spanned over 25 years. The telescope's iconic mirror is made of 18 hexagonal segments of beryllium, a material chosen for its lightness and stability at extreme cold. Each mirror was coated in a microscopic layer of gold and polished wrong on Earth, precisely calculated to deform into the perfect shape once it reached its freezing operating temperature a million miles away. Separating this ultra-cold mirror from the heat of the sun is a 5-layer sunshield, the size of a tennis court. With an effective SPF of 10 million, it creates a staggering 600-degree temperature difference between its hot and cold sides. For over 2 decades, thousands of people across 14 countries dedicated their lives to solving these impossible problems. The team endured budget cuts, congressional hearings threatening cancellation, and near disasters, including a direct hit from Hurricane Harvey during a critical test in Houston. They worked under the crushing weight of 344 single-point failures, any one of which could have ended the mission. They faced delays after screws came loose during vibration tests, and meticulously cleaned the mirrors by hand after they were contaminated with dust. It was a project that constantly teetered on the brink of failure. Finally, on Christmas Day 2021, the James Webb Space Telescope launched from French Guiana. But the launch was only the beginning. The real terror was the deployment, a robotic, unserviceable assembly in deep space. Over 29 days, the team held its breath as the sunshield unfurled and the mirrors clicked into place, and miraculously, it all worked perfectly. When the first images came back, they were more spectacular than anyone had imagined. The team was stunned to find that even in supposedly empty patches of sky, they were being photobombed by thousands of ancient galaxies never seen before. Webb revealed the stunning cosmic cliffs of the Carina Nebula, where new stars are born, and the glorious galactic dance of Stephan's quintet. The telescope became more than a scientific instrument. It became a source of global wonder, connecting people through a shared sense of awe. After decades of struggle, the James Webb Space Telescope opened its golden eye and is now showing us our universe and our place within it in a way we have never seen before. For decades, one of the greatest puzzles in physics has been the hunt for dark matter, the invisible substance that makes up 85% of the mass in our universe. Its story began in the 1930s, when astronomer Fritz Zwicky first noticed that galaxies in distant clusters were moving far too fast, held together by some unseen mass he called dunkel materie, or dark matter. But the idea was largely ignored for decades, until the 1970s, when astronomer Vera Rubin made an astonishing discovery. While studying the rotation of galaxies, she found that the stars on the outer edges were moving at impossible speeds, so fast they should have been flung off into the void. The only explanation was a vast, invisible halo of mass holding the galaxy together with its gravity. Her discovery launched a global search, leading us to today. Nearly a mile underground in South Dakota, the Lux Zeppelin experiment, or LZ, is now leading that search. It's hunting for a hypothetical particle called a WIMP, using a massive tank filled with 10 tons of ultra-pure liquid xenon as a trap, designed to catch the faint signature of a WIMP bumping into a xenon atom. After analyzing 280 days of data, the LZ collaboration has announced its new findings. The result? They found no evidence of WIMPs. But this is not a failure, it is a profound success. By finding nothing, the experiment has placed the most stringent limits ever on what dark matter could be. They have effectively told physicists, if WIMPs exist, they are not here, in this energy range we've searched. The team has dug deeper and more precisely than anyone in history, eliminating vast swaths of territory where this elusive particle could be hiding. And the hunt is far from over. The LZ experiment will continue collecting data for another 4 years, becoming even more sensitive. Beyond WIMPs, the detector's incredible precision allows it to search for other rare and exotic physics, from the decay of atoms to mysterious neutrinos from the sun. While the treasure of dark matter remains buried, the map is getting smaller. The Lux Zeppelin experiment is steadily closing the net, and with each null result, we move one giant step closer to solving the ghost story that began almost a century ago. In the grand theater of the cosmos, few ideas are as captivating as the wormhole, a theoretical shortcut through the very fabric of space and time. Born from the mathematics of Albert Einstein's general relativity, a wormhole is an Einstein-Rosen bridge, a tunnel connecting two distant points. Imagine folding a map so that your starting point and destination touch, then punching a hole through them. That's the idea. If they exist, we'd likely find these cosmic doorways in the most extreme environments imaginable, with the crushing heart of a black hole serving as a potential entrance. But there's a critical catch. Any natural wormhole would be catastrophically unstable, collapsing in on itself faster than light could pass through. It's a door that slams shut the instant it opens. To hold it open, we would need something straight out of science fiction. Exotic matter, a hypothetical substance with anti-gravity properties that could theoretically prop the tunnel open long enough for safe passage. And if we could build one, could we travel in time? Theoretically, yes. Here's how. Imagine creating a stable wormhole. You'd leave one mouth stationary, perhaps near Earth, and send the other on a journey at nearly the speed of light. Because of an effect called time dilation, time would pass much slower for the traveling mouth. When you bring it back, the two ends would be connected to the same location, but separated by years, or even decades. You would have a bridge connecting not just two places, but two different moments in time. Step into the younger mouth, and you'd emerge from the older one, arriving in your own past. Of course, this raises mind-bending paradoxes. Could you change history? Or would you simply create a new, parallel timeline? For now, wormholes remain on the far edge of physics. They are not something we have seen, but a profound what-if, born from our deepest equations, a tantalizing dream of a universe where the rules of distance and time might just be breakable. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were trying to use a large horn antenna in New Jersey. But they were plagued by a persistent, annoying hiss, a cosmic static they couldn't eliminate. They aimed their antenna at different parts of the sky. They checked their equipment. They even cleaned out the pigeon droppings inside the horn. But the faint, uniform noise remained. It seemed to be coming from everywhere at once. Unbeknownst to them, just a few miles away at Princeton University, a team of physicists was building a detector to search for the very thing they had accidentally found. It was the echo of creation itself. That persistent hiss wasn't noise. It was the oldest light in the universe, the afterglow of the Big Bang. We call it the cosmic microwave background, or CMB. Think of it as the baby picture of our universe. In its first moments, the cosmos was an incredibly hot, dense soup of particles and energy. Light was constantly bouncing off charged particles, unable to travel freely. But after 380,000 years, the universe expanded and cooled enough for atoms to form. Suddenly, the light was set free, and it has been traveling across the cosmos ever since, stretched by the expansion of space into the faint microwave glow we detect today. At first, this glow seemed perfectly uniform. But when our instruments became sensitive enough, they revealed a stunning, mottled pattern of tiny temperature differences, ripples that are only 1 part in 100,000. These ripples are the cosmic seeds from which all galaxies and galaxy clusters would eventually grow. And it's here, in these tiny ripples, that we find one of the most powerful pieces of evidence for dark matter. In the early universe, two forces were at war. Gravity was pulling matter together, trying to form clumps, At the same time, the intense radiation pressure of the hot universe was pushing it apart. For ordinary matter, the stuff that makes up stars, planets, and us, this created a sloshing effect, preventing it from clumping together too quickly. But dark matter is different. It feels the pull of gravity, but it doesn't interact with light at all. So while ordinary matter was being pushed and pulled by radiation, dark matter could quietly begin to clump together, unimpeded. It formed vast, invisible gravitational wells, a cosmic scaffolding waiting for the rest of the universe to catch up. When the universe finally cooled and the CMB was released, ordinary matter was free to fall into these pre-made gravitational blueprints laid down by the dark matter. The size, spacing, and intensity of the hot and cold spots we see in the CMB today are a perfect match for a universe where this invisible scaffolding gave ordinary matter a massive head start. Without the gravitational influence of dark matter in that first 380,000 years, the structures we see today simply wouldn't have had enough time to form. The baby picture of our universe isn't just a picture of light, it's a map of the invisible dark matter that shaped it. For years, biology has been a science of glimpses. We could see the individual parts of life's machinery, but understanding how they all fit and work together in a dynamic, intricate dance has remained one of science's greatest challenges. In 2020, DeepMind's AlphaFold 2 revolutionized biology by predicting the 3D structure of proteins, the building blocks of life, with astonishing accuracy. But that was only the beginning. Now, with AlphaFold 3, we are entering a new era. This isn't just an upgrade, it's a fundamental leap forward. Where AlphaFold 2 focused on proteins, AlphaFold 3 can see the entire molecular stage. For the first time, a single AI model can predict the structure and, crucially, the interactions of nearly all of life's molecules: proteins, DNA, RNA, and the small molecules called ligands, which include many of the drugs we use today. The discovery is in seeing how these different parts connect. It's one thing to know the shape of a lock. It's another entirely to know the precise shape of the key that fits it, and how that key turns. AlphaFold 3 models this molecular handshake with incredible precision. For interactions between proteins and drug-like molecules, it shows a stunning 50% improvement in accuracy over the best traditional methods. It's like switching from a blurry photograph to a high-definition, 3D digital model of life in action. And this is where the future begins. The most immediate impact will be in drug discovery. Instead of years of costly trial and error in the lab, scientists can now rapidly screen and design new drug molecules on a computer, testing how they will bind to a target protein with unprecedented accuracy. This promises to dramatically accelerate the development of new medicines and therapies, but the vision extends even further. By understanding how proteins interact with DNA, we can unlock deeper secrets of the human genome and how genetic variations cause disease. Beyond medicine, this technology opens the door to a new world of bioinnovation. Imagine designing novel enzymes that can break down plastic waste, or creating more resilient crops by modifying the proteins that help them withstand drought. To fuel this future, Google DeepMind is making this power accessible. They have launched the AlphaFold Server, a free and easy-to-use platform that allows scientists all over the world to model these complex molecular interactions. It's not just a breakthrough, it's a tool being shared with the global community. AlphaFold 3 gives us a new, powerful lens to look at the biological world. It allows us to move from observing what life is to understanding how it works, and ultimately, to engineering new biological solutions for some of humanity's greatest challenges. The dance of life has never been clearer. What if the star next door exploded? Alpha Centauri, our closest stellar neighbor, sits just over 4 light-years away. If it were to die in a supernova, it would trigger a cataclysm for Earth, unfolding in 2 devastating waves. The event itself would be silent to us, a star collapsing and then erupting in a blaze of glory. For 4.3 years, The light and radiation would travel across the void, an invisible messenger of doom. Then, it would arrive. The first thing we'd notice would be the light. A new star would appear in our sky, a blazing jewel of impossible brightness, thousands of times more brilliant than the full moon. It would be easily visible during the day, a second, malevolent sun. But the visible light is the least of our problems. Traveling with it is a silent and deadly wave of high-energy radiation, a torrent of gamma rays and X-rays. As this wave strikes our upper atmosphere, it would act as a cosmic executioner. The radiation would rip apart air molecules, creating chemical compounds that would obliterate our planet's ozone layer. Within months, Earth's protective shield would be shredded. Unfiltered ultraviolet radiation from our own sun would pour down, scorching the surface. Phytoplankton in the oceans, the very foundation of the marine food web and the source of most of our oxygen, would die off. Ecosystems on land and sea would collapse. It would be a mass extinction event, triggered from light years away. And this is only the first wave. Hundreds of years later, the second wave would arrive. The supernova's physical debris, a colossal expanding shell of superheated gas and heavy elements, traveling at a fraction of the speed of light, would slam into our solar system. Earth's magnetic field would buckle and fail under the relentless assault. This cosmic sandblaster would begin to strip our atmosphere away, peeling it back into space over centuries. Without an atmosphere, the oceans would boil away, and our world would be rendered a sterile, airless, radioactive rock. Fortunately, this apocalyptic vision is pure science fiction. The stars of Alpha Centauri are far too small to ever go supernova. Our stellar neighborhood is, thankfully, a quiet one, but it serves as a powerful reminder of our place in a universe that is as beautiful as it is violent. The story of the hydrogen bomb begins not with a bang, but with a flicker of terrifying possibility. In the crucible of World War II, the Manhattan Project gathered the world's greatest minds to unlock the atom's core. Their success, and the devastating use of atomic bombs on Hiroshima and Nagasaki, proved humanity could wield the power of nuclear fission. But for some, this was merely the first step. The end of the war did not bring peace, but a new, colder conflict. When the Soviet Union detonated its own atomic bomb in 1949, a new and horrifying chapter of the arms race began. In the United States, influential physicists like Edward Teller argued that a far greater weapon was not just possible, but necessary. They called it the super, a weapon that would work not by splitting heavy atoms apart, but by fusing light ones together, mimicking the very process that powers the sun. The result was a design of diabolical elegance. The core concept, known as the Teller-Ulam design, used the immense radiation from a fission bomb, an atomic bomb, as a trigger. The A-bomb would act as a matchstick, creating the millions of degrees of heat and crushing pressures needed to ignite the fusion fuel, unleashing 1,000 times more energy. After a series of tests, the United States prepared for the ultimate demonstration. The goal was to create a dry-fuel thermonuclear weapon, one that used a solid compound, lithium deuteride, making it small and light enough to be delivered by a bomber. The device was codenamed Shrimp, and the test was named Castle Bravo. On March 1, 1954, at Bikini Atoll in the Pacific, Shrimp was detonated. A silent, blinding flash gave way to a monstrous sun that bloomed over the ocean. The fireball swelled to over 4 miles wide, boiling the sea itself and vaporizing the test island and 2 others nearby. But in that flash of creation, there was a terrible miscalculation. Scientists had assumed that only one isotope of the lithium fuel would participate in the reaction. They were wrong. A second, seemingly stable isotope also reacted, unexpectedly breeding more fusion fuel and nearly tripling the bomb's power. A planned 6-megaton device became a staggering 15-megaton blast, 1,000 times more powerful than the bomb that destroyed Hiroshima. The consequences were immediate and horrifying. The massive fireball dredged up tons of pulverized, irradiated coral from the seabed, blasting it into the stratosphere. This created a vast, deadly cloud of radioactive fallout. 100 miles away, the crew of a Japanese fishing boat, the Daigo Fukuryu Maru, or Lucky Dragon, was showered in a strange white ash they called death ash. They had no idea they were being lethally poisoned. The radioactive cloud spread across the globe, detected in Australia, India, Japan, and the United States, proving nowhere on Earth was safe from the consequences. Castle Bravo was more than a test. It was a horrifying lesson. The genie of thermonuclear fire was out of the bottle, and the world would forever live in its shadow. For most of human history, our vision of the cosmos was surprisingly small. The Milky Way galaxy, with its brilliant river of stars, was thought to be the entire universe, a vast, solitary island of stars adrift in an endless, empty void. Dotted among its stars were faint, blurry patches of light called nebulae, believed to be swirling clouds of gas or solar systems in the process of formation. The most famous of these was the Great Andromeda Nebula. To the naked eye, it was a faint smudge. Through a telescope, a beautiful, mysterious spiral cloud. For centuries, astronomers debated its true nature. Was this nebula a nearby cloud of gas, a cradle for new stars within our own cosmic home? Or was it something far more profound? The debate came to a head in the early 1920s. The key to solving the mystery would be a new cosmic yardstick discovered by the brilliant astronomer Henrietta Swan Leavitt. She had found that a certain type of star, called a Cepheid variable, pulses at a rate directly related to its true, intrinsic brightness. They were perfect, standard candles. If you know how bright a light truly is, you can tell how far away it is just by seeing how dim it appears. Using the powerful new 100-inch Hooker telescope at Mount Wilson Observatory, an astronomer named Edwin Hubble began a meticulous study of the Andromeda Nebula. Night after night he aimed the telescope at Andromeda, painstakingly capturing its faint light on photographic plates. Then he found it, a single pulsing point of light within the nebula, a Cepheid variable. Hubble measured its pulse rate to determine its true brightness, then compared that to how dim it appeared. The calculation that followed would forever change humanity's place in the universe. The numbers were staggering. Andromeda wasn't thousands of light years away, nestled within our galaxy. It was nearly 1 million light years distant. It couldn't possibly be inside our galaxy. It was an island universe of its own, just as vast and magnificent as our own Milky Way, populated with hundreds of billions of its own stars. In an instant, the known universe didn't just get bigger. It shattered and reformed into something incomprehensibly vast. The walls of our cosmic home came crashing down. We were not alone in an island universe. We were just one island in an endless cosmic ocean, filled with countless other galaxies stretching out to the limits of our sight. That single discovery transformed cosmology forever. Today, we know there are hundreds of billions, perhaps even trillions, of galaxies in the observable universe. And it all began with one man, one telescope, and one faint fuzzy patch of light that taught us our true place in the cosmos. In the long, quiet history of our search for company in the cosmos, there are few moments as tantalizing or as fleeting as the wow signal. For 72 seconds, it was a thunderous shout in the cosmic silence, a mystery that remains unsolved to this day. The story begins on August 15, 1977, at Ohio State University's Big Ear Radio Observatory. The telescope wasn't a sleek, modern dish, but a massive, stationary array that used the Earth's own rotation to scan the heavens for signs of extraterrestrial intelligence. Its data wasn't displayed on a glossy screen, but printed on long sheets of computer paper. A few days later, a volunteer astronomer named Dr. Jerry Eman was reviewing the printouts. The paper was filled with the usual noise of the universe, a random peppering of low numbers representing background radiation. But then, Eamon saw it. A sequence of letters and numbers that shot off the page. 6EQUJ5. In the observatory's code, these weren't random characters. They represented signal strength. A 6 was 6 times stronger than the background noise. An E was 14 times stronger. And U was over 30 times stronger. It was a signal of astonishing power. It flared up, peaked, and then faded away exactly as expected for a source passing through the telescope's narrow beam. It was the perfect profile. Stunned, Eamon grabbed a red pen, circled the sequence, and wrote a single famous word in the margin: "Wow." So what was it? The signal had all the hallmarks of a potential alien beacon. It was extremely narrowband, meaning it was focused on a very specific frequency, something rarely seen in natural cosmic phenomena, which tend to be messy and broad. And its frequency was 1420 megahertz, the hydrogen line. This is the frequency at which neutral hydrogen atoms, the most common element in the universe, emit radiation. Scientists had long theorized that an intelligent civilization might use this fundamental frequency as a cosmic hailing channel. The signal came from the direction of the constellation Sagittarius. But the problem, and the heart of the mystery, is that it was never heard again. Astronomers have revisited that exact patch of sky thousands of times, with more powerful telescopes. They've found nothing. Hypotheses have been proposed over the decades. Could it have been a signal from Earth bouncing off a piece of space debris? Possible, but the signal was in a frequency band protected for astronomical use. Could it have been the hydrogen cloud from a passing comet? A later theory suggested this, but further studies have found it unlikely to produce a signal that's strong and focused. And so the "wow" signal remains a ghost in the machine. A 72-second cosmic question mark. Was it the fleeting transmission of a distant intelligent race? A bizarre, 1 in a trillion natural event? Or simply the strangest piece of noise we've ever recorded? We may never know. But it stands as a powerful, humbling reminder that out in the vast, silent dark, there are still wonders waiting to be found. There are moments in history when a challenge is so immense, it redefines what is possible. In the throes of the Cold War, a race to the heavens became the ultimate expression of national will. The goal, set forth by a president and embraced by a nation, was audacious, almost unthinkable: to land a man on the moon and return him safely to the Earth. This was the promise of the Apollo program. It was a monumental effort, a symphony of engineering and human courage. At its heart was the towering Saturn V, the most powerful rocket ever built, a 36-story giant designed to break the bonds of Earth's gravity. The program advanced in a series of daring steps, each mission building on the last, pushing the boundaries further. It was a path paved with both triumph and tragedy, forever marked by the fire of Apollo 1, a stark reminder of the razor-thin margin for error. Then came July 1969. The world held its breath as Apollo 11, with Neil Armstrong, Buzz Aldrin, and Michael Collins aboard, made its historic journey. 4 days after leaving Earth, a small, spindly craft named the Eagle descended toward the lunar surface. The crackle of Armstrong's voice through the speakers confirmed the dream had become reality. "Houston, Tranquility Base here. The Eagle has landed."
Houston, Tranquility Base here. The Eagle has landed.
Soon after, humanity took its first steps on another world, a giant leap for mankind. But the moon is an unforgiving frontier. Less than a year later, Apollo 13 turned from a mission of exploration into a desperate, brilliant scramble for survival. 200,000 miles from home, an explosion crippled their spacecraft. The calm, chilling words, "Houston, we've had a problem," set in motion one of humanity's finest hours. The lunar landing was abandoned. The new mission was simply to get the 3 astronauts home alive, using their lunar module as a lifeboat. Through sheer ingenuity in space and on the ground, they did it. Apollo 13 became the program's successful failure. The missions continued. Astronauts on Apollos 14 through 17 drove lunar rovers across alien planes, conducted vital experiments, and brought back a treasure trove of scientific data. But in December of 1972, the final footprints were left in the dust. The Apollo program was more than a series of missions. It gave us new technology, a new understanding of our solar system, and a new perspective on our own fragile planet. It stands as an enduring testament that with enough courage, vision, and collective will, even our most celestial dreams can be brought within our grasp.